In our last video, we looked at the basics of, or really the introduction to multiple regression. We looked at the model, how to specify that model. We, or at least I, estimated a multiple regression equation, put it on the board, and we talked about how we're going to do that estimation through computer software because at this level it's a little bit too complex. Then we went on to talk about how we interpret those coefficients and very briefly talked about using that model, using that regression equation to estimate or predict our dependent variable. What we're going to do today, or in this video I should say, is we're going to look at model evaluation. So we're going to look at a couple ways for us to evaluate our model, and depending on time we might get into the individual coefficients as well. So the first way we're going to evaluate our model is something that we've already seen. We're going to look at what's called goodness of fit. And when checking goodness of fit, the thing that we most often go to is our coefficient of determination, or as it's more commonly called, the R squared. So hopefully we remember this from our videos on simple linear regression. It's the same setup. R squared is the ratio of explained variation to total variation. So SSR, that's our sum of squares regression. That is the variation explained by the model. Our TSS, that's our total sum of squares. So this is the total variation in our dependent variable. And of course we can also solve this by doing 1 minus the sum of squared errors divided by the total sum of squares. Also, hopefully we remember, even though I kind of shoehorned it in there at the last second, that our R squared, it is a ratio, so it's always going to be between 0 and 1. It can, I guess technically it can equal 0 and it can technically equal 1. That's very rare. That's not going to happen very often, right? But it has to be between those two numbers. If it is above 1 or below 1, that's a red flag. We may have made a mistake. We need to go ahead and check our work. All right. The interpretation of R squared is the R squared times 100%, because remember R squared is going to be a decimal value, so to get into that percentage we multiply it by 100. So it's that percentage of variation in the dependent variable that's explained by the model. In simple linear regression, I said you could just say that it was the percentage of variation explained by the independent variable. That's no longer the case because we don't have just one independent variable. We're going to have multiple, hence multiple regression. So we do have to stick with the model. So it's the percentage of variation in the dependent variable explained by the model. So in the previous video for this chapter, we looked at a regression equation. We were trying to use years of education and years of experience to predict hourly wages. So for that equation, our total sum of squares, so the total variation for our dependent variable hourly wages, was 164,565, and our sum of squares regression was 32,190. So with this information we can calculate our sum of squares. We can calculate our R squared. So our R squared is going to be calculated as 32,190 divided by 164,565. Once we punch that into our calculator, we should get 0.196. So when we're interpreting this, of course, we would, to get it to that percentage, we'd multiply this 0.196 by 100. But we could interpret it as 19.6% of the variation in hourly wages is explained by the model. So that is our interpretation for R squared. Now, there are some other considerations. This is not the only measure for goodness of fit. We're about to talk about another one, and by about to, I mean we're going to do that right now. So this is the only thing that we looked at with our simple linear regression, but now that we're in multiple regression, there's another measure for goodness of fit that we're going to talk about, and this is what's known as the adjusted R squared. What the adjusted R squared is doing, or what it's here for, is because whenever we add independent variables into our model, we're going to increase the amount of variation that's explained, right? Even if it's just a little bit. So if we continue to add independent variables, we're going to, whether we mean to or not, inflate the value of R squared. So to counteract this, right, and actually let me explain that a little bit better. The reason for this is because even if we add an independent variable that doesn't have anything to do with the dependent variable, it's still information. And that information is going to increase the explanatory power of the model, whether that variable really should be in there or not. Right? And this is a problem, of course. We don't want somebody to be able to put in the number of dogs somebody owns into a wage equation and that increase the expected, or the amount of variation that's explained by the model, right? There's no reason to believe that how many dogs the person owns impacts their wages, right? If anything, the relationship would be opposite, right? Your wages would be more likely to impact the amount of dogs you own, but that's neither here nor there. The point is that by just throwing in more variables, we can increase that R squared. So that's where the adjusted R squared comes into play. This is the formula for the adjusted R squared. You might see this written a couple of different ways. Minitab is going to write it as ADJ R squared. A lot of other software packages do that as well. But you might see it as R squared with a subscript A. That is another, right, if you see that, that's another way people will notate this. I think this is the way your book notates it as well. So here we can see it's a little bit more complicated, and again, that's because it is trying to do something a bit more complicated. Now, the way this works, and the reason that we're using kind of that 1 minus SSE over TSS formula with a slight addition is for this reason, right? If we look at this term, right, this term is the only thing we're adding to the calculation for R squared, or one of the calculations for R squared. So what this term does, this n minus 1 over n minus k minus 1, is that as k increases, right? So all else equal, if k is increasing, then this denominator is getting smaller, which makes the term as a whole larger, right? And so when we multiply that larger number by the kind of ratio of error to total variation, right? Error variation that's just random variation to total variation, it makes that ratio larger. So then when we subtract it from 1, we're getting a smaller number, right? So as you increase your independent variables, or the number of independent variables, right, you're going to make this term bigger, right? It's going to make the weight, right? It's going to weight the random error more heavily, the random variation more heavily, so that it looks as though, right, or that so that we can see, kind of get an idea of how much explanatory power we actually have, right? And to take into account those added independent variables. Right. Also, you'll notice that, or you may or may not have noticed, that if we increase n, that's going to mitigate some of those effects. So it's going to be something that we're going to talk about, probably not in this video, but in a one in this series, right? The larger your sample size, the more independent variables you can have without that being as much of a problem, right? That inflation of your R-squared, inflation of your explained variation, right? That variation explained by the regression. All right, but there is our formula. All right, before we actually look at an example and actually work one of these out, let's talk about interpretation. So unlike R-squared, the adjusted R-squared has no interpretation. The reason for this is because once we include this term right here, this adjustment term, n-1 over nk-1, we're no longer looking at a ratio of explained to total variation, right? That's what R-squared is. It's a ratio, right? And so we can interpret it as a ratio. We can talk about it in percentages, so on and so forth. We cannot do that with the adjusted R-squared because it's not a ratio. You can have an R-squared, again, this is not going to be very common, but you can have an R-squared that is, less. You could have a negative R-squared theoretically, right? If this term gets large enough, then that could happen. It's not going to, but it could, right? So it's no longer that ratio. So a lot of times you're going to see the adjusted R-squared reported as a percentage, and a lot of times people are going to interpret the R-squared, the adjusted R-squared, as a percentage, as the percentage of variation explained. Technically, that is not correct, and they shouldn't do that. But they still do. But technically, again, it's not a ratio. It's just there for comparison among other. One, it's used to compare that adjusted R-squared to your actual R-squared, see if there's a huge difference. If there is, you might want to think about that. But also used to compare between multiple different regressions, right? So you might be trying a bunch of different things in regressions, right? Inserting certain variables, removing others, trying to find the one that predicts the best. And so if you are doing that, you might look at that adjusted R-squared, compare those and see which one's highest. The one that's highest, of course, would be the one that's best because it has the best fit, right? But again, we can't technically, in reality, you can do whatever you want, but technically you shouldn't interpret this as percentage of variation explained. Let's see if we can just do this. I don't think it's going to take up that much space. So again, looking at our model, our wage equation. Right, probably not surprising. The total sum of squares hasn't changed. We're also going to need our sum of squares error, which is going to be 132,000. 375. We're going to also need our sample size, which for this data set is 1,000. And we're going to need to know what K is. So just as a reminder, K is the number of independent variables. In this model, we are using years of education and years of experience to predict wages. So that means we have two independent variables, so our K is equal to 2. Probably going to need a little bit more space than I thought we would, but here we go. So our adjusted R squared is equal to 1 minus, right, now we need to include that term, that n minus 1 over n minus k minus 1. So n minus 1 would be 999 divided by n minus k minus 1, 1,000 minus 2 minus 1, so 997. And we're going to multiply that by the sum squared error. So 132,375 divided by our total sum of squares, which will be 164,565. All right, so here we can see that this is not going to be much different from 1. Part of that is because we only had 2 independent variables, so our K was pretty low, and our sample size is pretty high. It's 1,000. So this is not going to make a huge difference. It's going to make a slight difference, but it's not going to make just a terribly large one. All right, so regardless, once we put all of this into our calculators, we're going to get 0.194. All right, so comparing that to our regular R squared of 0.196, it went down a little bit for that extra variable, but you know, it's not that big of a difference. Once you get out and you need to start reporting either the R squared or the adjusted R squared, it's going to depend, you know, which one you pick is going to depend on industry standards, kind of what your bosses expect you to report, so on and so forth. But for my money, unless there's just a real big reason not to, I always prefer to report the R squared just because it's easier to interpret. You actually get, well, you just can interpret it. Whereas with the adjusted R squared, that's not something we can do. Suppose I should really say that's not something we should do, not that it's something we can't do, because again, people do it. Okay, so the next thing we're going to talk about, again, talking about the model, and now talking about something completely new. This is a test for model significance. All right, so what does it mean for our model to be significant? What this means is that at least one of our independent variables actually has an effect on the dependent variable. All right, so if at least one of them is kind of at least one of those betas is not 0, right? Whether it's positive and has a positive effect or negative and has a negative effect, right? Either of those cases is fine for us to have significance, right? If none of the independent variables have any effect, then all of the betas will be 0, or at least the slope betas, 1 through k. Right? And so that's what we're testing for. Right? Actually, let's just kind of illustrate that a little bit. All right, so this is our model. It's the model we have been using, right? And so when we're talking about significance, right? If this model is significant, it means again that one of these two variables has an effect on it, right? So either years of experience or years of education or years of experience will change wage, right? So beta 1 and beta 2, they can't be 0, right? If it's 0, nothing happens, right? And we can illustrate that by if we say, if this equals 0, all right, if beta 1 equals 0 and beta 2 equals 0, then it doesn't matter what number you put in here for education, that term is going to be 0. And it doesn't matter what you put in here for experience, that term is 0. So the only thing left is beta naught. Well, and that doesn't tell us anything, right? It just tells us that, you know, wages are equal for everybody, or it's just giving us the average for the wages. All right, that's not useful, that's not good. So we want to test to make sure that at least one of these does not equal 0. So the way we do this is gonna look like pretty much every other hypothesis test that we've done. We're gonna start with a null and alternative hypotheses. All right, so our null hypothesis is what we're going to assume to be true, and in these cases we're going to assume that the model is insignificant, that our independent variables do not have any explanatory power when it comes to the dependent variable, or the betas, the slope betas, are equal to 0, all right? So that's what we're going to assume, so that's what our null hypothesis is going to be. Okay, so in a kind of generic form, the null hypothesis will be beta 1 equals beta 2 on to beta k, and they all equal 0. The alternative hypothesis is going to be at least 1 does not equal 0. Now, a couple of things before we move on to the next step. The next step would be specifying your alpha. We're going to kind of skip that and go to the critical value stage. But before we do that, I want us to talk about a couple of things. Right? One, this should look somewhat familiar. Not exactly familiar, but some. I guess, can you be exactly familiar? Anyways, that's not important. Right? This should look familiar. Right? We've got multiple parameters, right? We've got multiple equal signs. This is very much like ANOVA, right? When we were doing ANOVA, we were looking at the difference between the means, and seeing if those means were all equal to one another. Right here, we've got all of our betas, right? Beta 1 through k, they're all equal, and then they're all equal to 0. All right, then our alternative hypothesis, at least 1 does not equal 0. That's very similar to at least 1 is different, which was our alternative hypothesis for the ANOVA tests. Right? All this to say that the distribution we're going to be using is the F distribution for this. Right? So again, if you remember, when we have multiple equal signs in our equation, in our null hypothesis or in our hypotheses in general, that's a big indication that we should be doing an F test. All right. So our critical value, it is an F. So our critical value is F. Then our significance level alpha. Then we, if we remember, have 2 degrees of freedom for an F test. Here, our degrees of freedom are k, right? The first degrees of freedom, df1, that's k. It's the number of independent variables. And df2, or degrees of freedom 2, is n minus k minus 1. All right, then we will have our f-stat. The numerator of our f-stat is the sum of squares regression divided by the number of independent variables, or k. And our denominator is the sum of squared errors divided by n minus k minus 1. All right, so again, this should look somewhat familiar. Our test statistic when we were doing ANOVA was MST over MSE, right? So our sum of squares treatment divided by their degrees of freedom, right? Which is k minus 1. Here, that's exactly what's happening as well in the denominator, right? Sum of squares regression this time instead of treatment, but it's still that explained variation, right? Divided by its degrees of freedom, k, right? We also hopefully remember from ANOVA that whatever we're dividing by in the numerator in our test statistic is our degrees of freedom for the first degrees of freedom. All right, similarly down here, we have the sum of squares error divided by its degrees of freedom, n minus k minus 1, and that's pretty much exactly, slightly different, but very similar to what we had in the denominator of our test statistic for ANOVA, which was the mean squared error, or sum of squared error divided by nt minus k. I believe that was the degrees of freedom, right? So again, very similar. It's an F test. It's very similar to what we did in ANOVA. All right, slight differences, but this is our F test, right? And I'm not going to actually write this down because I think you can easily write this down. Actually, no, I am going to write it down. So we've got all of our steps, right? That's all of our steps except for one, which is stating our conclusion. You guys probably have already figured out how these work because it's exactly the same as ANOVA. All right, also if we remember, this is what our F distribution looks like. So really we're always just going this way, at least everything we're doing in this class. So if the test statistic, if our F-stat is greater than the critical value, it falls in the rejection region and we're gonna reject the null hypothesis. All right, so that's our kind of conclusion criteria for this F test. Alright, so with that in mind, we are going to perform our own test. I'm going to assume that either you've already written down the numbers that we're going to need, or you can go back and find them. So again, we're going to test this model we've been working on this entire time, right? Wage being regressed on, or yeah, we're regressing wage on experience and education, right? So when we start our test, right, we start with our null hypothesis, right? That's all of our slope betas, all right, or slope coefficients, or slope parameters rather, equal 0, all right? We have 2, right? Because we have 2 independent variables, years of education and years of experience. Right, beta 1 equals beta 2 equals 0. All right, and then our alternative hypothesis, I wrote this slightly differently, but it gets the point across, right? At least 1 is not 0. I started to do the ANOVA alternative, but you know, it's all right. So 1 does not equal 0, at least 1 is not equal to 0. However you want to write it, that's fine. Then we need to find our test statistic. We're going to just use 5% for our significance level, so our alpha is 0.05. Then we go to our degrees of freedom. The first is k, the number of independent variables we have. Right, we know that we have 2. So that's what our degrees of freedom are. And then our second degrees of freedom are n minus k minus 1. If we remember from earlier, n is 1000, k is 2. So 1000 minus 2 minus 1 is going to give us 997. All right, and of course, 997 is way higher than any of the DF2s on the chart that you have access to. So we're just gonna, use the infinite degrees of freedom for those second ones. So our critical value is approximately 3. Then we will go to calculate our f-stat. So in the numerator, it's going to be our SSR, which is 32,190. We're going to divide that by k, which is 2. Then in the denominator, we're going to take our sum of squares regression, our sum of squares error, our SSE, which is 132,375. And we're going to divide it by n minus k minus 1, which we know, right, is 997, mainly just because we just did it for our degrees of freedom. So once we have that in place, we're going to go ahead and punch it into our calculators, and we're going to get 121.22. All right, so we probably don't really need to do much else with this one. We're probably going to figure out what the conclusion is, but 122.22 is definitely larger than 3.0, so our conclusion will be that we reject the null hypothesis and conclude that the model is significant. All right, so that is how we are going to evaluate our models. We're going to go ahead and stop there, try to keep these videos at a palatable length. In the next video, we're going to be looking at evaluating our individual betas. I don't know why I'm being coy about it. We're going to look at hypothesis testing for individual betas. We'll also briefly look at confidence intervals for those betas as well. All right, I will see you guys in the next video.